Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole.
And I'm Brian, and we're both from Calgary, Alberta, Canada.
Thanks again to our Patreon subscribers. We really appreciate your support.
For significantly less than the cost of Farm Simulator 2022, which I downloaded over the weekend and spent far too much time playing, at least more time than I'm willing to admit, you can get to hear us talk about way more interesting engineering failures.
That's $5 Canadian a month, inflation proof, so it's not changing. And you get to hear us talk about twice as many interesting engineering failures. And we have, I would say it's a little bit more loosey-goosey with the format over there. Still engineering failures, still interesting, but I think we have a little fun with it.
We do indeed, and you could even listen to it in your tractor when you're doing stuff in Farm Simulator.
I thought you meant your actual tractor, and I was like, do tractors have Bluetooth?
Some of them do. Some of the tractors do have Bluetooth.
Yeah, that would make sense. My brain went down a whole rabbit hole, though, but I came back. Don't worry, I'm back.
All right.
Shall we talk about the news?
We should talk about the news, because this week in engineering news, we're going to talk about microplastic magnets in water. Researchers at the Royal Melbourne Institute of Technology, that's the RMIT, not to be confused with MIT, the Massachusetts Institute of Technology, in Australia, have developed magnets to attract and remove microplastics in water in a fraction of the time compared to traditional methods. Using absorbents in the form of powder, they can remove microplastics that are 1,000 times smaller than what can be removed by wastewater treatment plants. Microplastics smaller than 5 millimeters are not detectable and take 450 years or more to degrade. The absorbents made from a nanopillar structure are made from recycled waste and can be reused. So they're breaking stuff down, recycling things, and they're made to reuse stuff. It sounds like a win-win-win-win situation. The nanomaterials contain iron, which can then be picked up by magnets, so the absorbents attract the microplastics, and the magnets attract the absorbents, and everyone wins.
Well, they've now detected microplastics inside humans. The microplastics, I mean, they're really small, so we can't see them. We don't know they're there, but we're likely drinking them or eating them, depending on where they're coming from. And so this is really good news that they can remove it, because at least we have a chance to prevent ourselves or mitigate the amount that we're digesting. It's said that this process to remove the microplastics takes about an hour, but I'm assuming that depends on the size and how well the absorbents mix with water. But like I said, this is a big step in the right direction for cleaning up our water and reducing the amount of microplastics that we're ingesting. If you want to read more about the study, check out the link on the webpage for this episode at failurology.ca.
What's the first thing you think of when people approach you on the street?
Well, mostly the audacity.
Hey, isn't that an audio recording program?
It is, but they don't sponsor this podcast. If they did, though, this week's episode of Failurology would be brought to you by Audacity.
Now on to this week's episode. If you've been with us for a while, you already know this. If you're new to the show, thank you for joining us. Every 10th episode, we talk about an engineering marvel instead of a failure. And when we created the show, we thought this was just a fun way to keep things interesting and talk about really cool things that are going on in the world of engineering. So with this being episode 70, this is our 7th marvel that we've covered. And among a few space ones that we've talked about, we're kind of working our way through the American Society of Civil Engineers' 7 Wonders of the Engineering World. The marvel that we're going to talk about today is the Golden Gate Bridge. So far on that list, we've talked about the Channel Tunnel, the Panama Canal, the CN Tower, and the Golden Gate Bridge is next. And there's a few others on the list that we hope to cover in the future. If you're thinking, it's just a bridge, it's not that fancy, how can it be on this list? I'll admit I wondered that myself at first, but it's the size of the bridge, or more importantly, its length, the span across the body of water, and the era that it was built that makes it so impressive. It's also really pretty, and it's very photogenic, and one of, if not the most photographed bridge in the world. In fact, I was in San Francisco in 2012, and I took several photos of it myself. Brian, have you been to San Francisco?
I have been to San Francisco, and I've actually been at the Golden Gate Bridge. Unfortunately, I was at the Golden Gate Bridge during rush hour time, So instead of crossing the bridge in rush hour traffic, I decided I would park my car and take my bike off because I had my bike with me at the time. So I just rode my bike across the Golden Gate Bridge, and that seemed like a much better use of my time than sitting in traffic in rush hour traffic. So I was just driving through San Francisco at the time. I don't think I spent the night in San Francisco, but I've been across the Golden Gate Bridge both in my car and on my bike. And I've always thought it was a super, super cool bridge. There are a couple of aviation incidents of people flying underneath the bridge from various eras in aviation. I've always thought that is kind of cool to fly underneath the bridge. I personally would never do it. It's
Sounds
very unsafe.
dangerous.
Please don't do that. It is very dangerous. But the video footage that exists from some people flying underneath it, as well as some of the photographs of people flying underneath it, for military and civilian aviators, they make some pretty cool pictures. But again, please do not fly an airplane underneath the Golden Gate Bridge. No matter how cool you think it might be, it is a huge risk to health and life of people and yourself. Please don't do that. And the FAA probably will not be very happy with you, and they will likely suspend your license or cancel it altogether.
Back to the bridge. So the Golden Gate Bridge is a suspension bridge, and it got its name because it spans the Golden Gate, which I didn't even know was a thing until I started researching this. So the Golden Gate is a 1.6 kilometer or 1 mile straight that connects the San Francisco Bay with the Pacific Ocean. I've always thought the geography of San Francisco was interesting, and either I had somehow missed the Golden Gate entirely as I was reading up on San Francisco's geography in the past, or I did learn about it and completely forgot. But I've always thought it's really interesting, and San Francisco's kind of like a Y. You have San Jose at the bottom, and then the west part of the Y, as you go up towards the west or to the left, is San Francisco, and then the east part is Oakland and Fremont. So San Francisco itself is built on a peninsula. And the Golden Gate Bridge takes you from the northern end of that peninsula across into wine country. There's also 3 other bridges that take you east from San Francisco into Oakland and Fremont. And while they are impressive in their own way, they're not the Golden Gate Bridge.
When the bridge opened in 1937, it was the longest and the tallest bridge in the world, with a main span, or the main part of the bridge that goes over the water, of 1,280 meters. It's 4,200 feet, which is, to me, that's a very impressive distance. Like, that's 2/3 of a mile off the top of my head. I guess 2/3 of a nautical mile. Over 75% the length of a mile. Like, this is a long bridge. It also had a height of a very impressive 227 meters, or 746 feet, which is basically equivalent to a 75-story building. So the clearance height on the bridge deck is 4.3 meters, or 14 feet, which is not quite tall enough for trucks, so they have to take a different route. The clearance below the bridge is 67.1 meters, or 220 feet at high tide. For reference, several cargo ships and some cruise ships can pass under the bridge, and for something of a similar era, the Titanic would have fit underneath the Golden Gate Bridge. Unfortunately, as we all know, it never made it to San Francisco.
Not even close.
Not even close.
That said, we've talked about the Titanic on episode 11, I think, and it was actually pretty interesting if you want to check it out.
Today, the Golden Gate Bridge is the 19th longest bridge and 40th tallest bridge in the world, which I think is super impressive because it's 80 plus years from the time it was constructed, and it's still in the top 20 for the longest bridge and top 50, I guess top 40 for tallest bridges in the world. So I think that's super impressive. Despite appearing to be red, though, the bridge is actually an orange vermilion called International Orange, and the color was chosen because it blends in really well with the natural surroundings there, but it's easily visible in the fog, which is pretty important for a bridge near San Francisco, especially a bridge that was built before GPS technology was a thing, before Loran-C was a thing, before a lot of modern navigation methods were really a thing. So being able to see the bridge, pretty important back in the 1930s. So the bridge deck itself carries 6 lanes of traffic and an eastern and western walkway for pedestrians and bike traffic, which is how I rode my bike across the bridge. I think the 6 lanes were pretty impressive for 1937. A lot of modern bridges don't have 6 lanes of traffic or 3 lanes each way. Unfortunately, we've seen that a lot of older bridges they wind up having to be retrofitted with additional lanes, or something has to be engineered to basically hang a lane off the original bridge infrastructure. But the Golden Gate Bridge had 3 lanes each way from the start, which is I feel it's very progressive for when it was built in 1937. On average, 118,000 vehicles cross the bridge every day, so there's quite a bit of volume that's going across this bridge. The weight of the bridge deck is supported by 250 pairs of vertical suspended ropes attached to 2 main cables passing over 2 main towers. Each cable is composed of 27,572 strands of wire. Each tower has approximately 600,000 rivets, which is a lot of rivets. Having done some riveting before, I could not imagine doing 600,000 rivets. That's a lot of rivets to do.
I've never done any riveting, and I still can't understand what that means. The bridge was built to provide a permanent link with the communities around the bay and improve the city's growth rate. There used to be a ferry service, but it took about 20 minutes per trip to get across the Golden Gate. The issue with the bridge that took them quite a while to build it, aside from competing with the ferry, was that it was such a long span. The water was really deep. There's strong swirling tides and currents. And those were all things that the bridge construction had to contend with. And so it took a lot of time to find a way to overcome all of those challenges within their budget. Speaking of budget, early estimates for the bridge had a cost of around $100 million US, which is equivalent to $2.5 billion US today. So, I mean, this bridge was built in 1937, so $100 million is a lot of money back then. But Joseph Strauss was an ambitious engineer, and he promised that his design could be built for $17 million US, which is 17% of what the actual estimated cost was. It took about 10 years to convince everyone that the bridge was necessary. There were concerns with shipping traffic. They didn't want to block the entrance to the main Navy harbor. There were guarantees for local workers to be used for construction. There was concern with competition to the ferry fleet. And there was also concern with increased traffic on the north side. One ally for the bridge construction, which is no surprise, was the automobile industry. And they saw the development of roads and bridges as an increase in the demand for cars. While Strauss was the chief engineer for the bridge project, after he finally convinced everyone to use his design and that he could build the bridge for cheaper, he continued to oversee the design and construction, but he had a limited understanding of cable suspension designs, and he referred to a lot of experts for this work, which is great that he recognized his weaknesses and called for help. And otherwise, this could be a completely different episode where we talk about a failure and not a marvel. So it's really good that he recognized that he was not good at designing cable suspension bridges, and he called in reinforcements.
Architect Irving Merrow designed the shape of the bridge towers, the lighting scheme, Art Deco elements, and the international orange color that we mentioned earlier. So basically everything that people recognize about the Golden Gate Bridge, Irving Merrow was the guy that designed all of that. The final suspension design was conceived by Leon Mosieff, who designed the Manhattan Bridge in New York City. Now that I've kind of looked at both of them, it makes a lot of sense. The two bridges, they have a very similar aesthetic. Different side of the country, similar aesthetic.
I think it's really interesting when you start to recognize similar designs around the world, and then you look them up to see if they were designed by the same people. I love puzzles, and so that always seems like a puzzle to me. One example is the architect Foster and Partners. They use this diagrid pattern of diagonally intersecting members on the outside of a building. And they did the Bow in Calgary, the Gherkin in London, the Hearst Tower in New York. They all have that same diagrid pattern on the outside. And so every time I see a building that has that same pattern, I look it up to see if they did that building. And it's a fun little puzzle and little things that you recognize. It's kind of cool. So the same thing happened here.
I feel it's like similar to painters. I feel every recognized painter has a certain style, and even if you don't know that the painting is done by a certain painter, if you look at the painting, you'd be like, oh, that looks very much like a Rembrandt painting. Then you find out it actually is a Rembrandt or something similar to that. But yeah, everyone's kind of has their own their own style, I guess, at some point. And it's really neat when you recognize, what you think is something that's done by a certain architect or painter or designer. Look it up, and it actually is done by that person. So I always think that's neat as well. Mosieff, though, created the basic structural design, which included his deflection theory, that is, a thin, flexible roadway that would flex in wind and reduce the stress placed on cables and towers. Mosieff also designed the Tacoma Narrows Bridge later on, which collapsed in a windstorm due to unexpected aeroelastic flutter.
Yeah, that one did not go well, and we're going to talk about it on an episode very soon.
Yeah, I feel the Tacoma Narrows Bridge is something that gets brought up a lot in engineering design courses. We certainly looked at it in a first or second year engineering design course. And yeah, like Nicole mentioned, we will certainly dive into it on a later episode that's coming up pretty quick on failurology. Charles Elton Ellis worked with Mosieff as the principal engineer of the project, completing a lot of the technical and theoretical work that built the bridge. Ellis also designed the Bridge with a Bridge on the south end to avoid demolishing Fort Point. He was fired in 1931 by Strauss for sending too many telegrams back and forth with Mosieff. Ellis went on to turn in 10 volumes of hand calculations and became a structural expert, writing the standard text of time, as well as being a professor of engineering. He was replaced by Clifford Payne. With the hopes of self-promotion and posterity, Strauss downplayed his collaborators' work, even though they were mostly responsible for the final form of the bridge and did so for little pay. Strauss died a year after the bridge was completed. In 2007, the Golden Gate Bridge District gave major credit for the bridge to Ellis.
Although he was unfortunately deceased at that time. Not because of the bridge or anything like that. So construction of the bridge finally began on January 5th, 1933, after decades of deliberations and looking at different designs and trying to make this work. Even though Strauss believed that his design could be completed for $17 million, when they actually went to build the bridge, the budget was closer to $37 million, but they ended up doing it for $35. And it also was completed ahead of schedule. So under budget and ahead of schedule, which I can assure you does not happen for construction projects anymore. And I think part of that is because the schedules and budgets are squeezed so tight that there's no room to come in under. But it's a nice feeling. I've had it happen like once or twice in my career. It's a nice feeling, but it's very rare. The steel company that was contracted to build the bridge, Bethlehem Steel, also made steel for the George Washington Bridge between New York and New Jersey, the Peace Bridge between Buffalo and Fort Erie, the Verrazano Narrows Bridge in New York City, the Hoover Dam, Madison Square Garden, Empire State Building, Merchandise Mart in Chicago, and Alcatraz Island, among so many other projects, before they filed for bankruptcy in 2003. So Bethlehem Steel was a major player in the construction industry throughout the United States for several decades, but unfortunately, they did not survive the early aughts. Strauss innovated the use of a movable safety net to catch workers who fell off the bridge, saving the lives of 19 men over the course of the bridge construction. And if you remember from the details Brian gave earlier, it's a long way down. It's quite a fall if you fell off the bridge. And fall arrest safety was definitely not where it is today. And so that safety net was a great innovation to keep people safe while they were constructing the bridge and prevent them from falling all the way into the water.
Yeah, like I feel at this era, I don't think we had dynamic rope at that point. We certainly didn't have any sort of like elastic or nylon type harnesses or webbing or really the health and safety standards that we do now. And I know some people are grumpy about fall protection, above 2 meters, but back then to save 19 lives in a project like this, where I feel if those 19 people had have died, it just would have been something that happens on a project. That's pretty cool because that's 19 people that got to go home to their families at the end of the day, and hopefully went on to live long and productive lives and do other cool things. So things like that, even though we don't think very much of them now as an innovation, somebody still had to invent them back in the day, and there was a time in construction when those weren't common to have.
Yes, and so while the netting did save 19 men, which is fantastic, on February 17th, 1937, so shortly just before the bridge was finished, A scaffold with 12 men on it and undersized bolts fell, and they broke through the netting. 2 of those 12 survived the fall. The netting could have used some improvement, but overall, I think it was a success. There were about 5,000 men working directly on the bridge at a time, which is a lot of people, and it took 31 million work hours in 134 cities and 20 states, which, with its timing related to the Great Depression, was enough of a boost to float the economy of the entire country. Parts and pieces for this bridge were being constructed in over 130 different cities throughout the US, situated within 20 different states. That work that came in at a time when there just wasn't work was enough to float the country during the Great Depression, which I think is kind of really cool and something that I had no idea of before I started researching this bridge. The bridge required so much concrete that they ended up reopening several cement factories that had closed during the Great Depression, and whole forests were cut down in Oregon to build the wood forms, which I'm less happy about. The bridge opened on May 27th, 1937.
Over the ensuing years since the bridge opened, the bridge has undergone some maintenance, which is great. Something that old and yeah, sure. Since the bridge opened in 1937, the bridge has undergone a number of rounds of maintenance, which is a very positive thing to have done to it. In 1953 and 1954, lateral and diagonal bracing was installed to connect the lower cords and the 2 side trusses to stiffen the bridge deck in torsion. A December 1st, 1951 windstorm revealed instabilities similar to the Tacoma Narrows Bridge. The original concrete bridge deck was replaced over 401 nights between 1982 and 1986 without closing the roadway completely. The concrete had been exposed to the salt carried by fog or mist and was corroding the rebar and spalling the concrete. During this project, the roadway was widened 2 feet, which gave a wider outside curb lane. The deck replacement cost $68 million US, which, if you deflate that value back to $1937, represented about 1/3 of the total bridge cost, which I feel is kind of on par with where I would think it would be. The bridge deck makes up a lot of the structure, not all the structure. Yeah, 1/3 seems about right. 1/4 to 1/3.
In the early 60s, the Bay Area Rapid Transit, also known as the BART, and as you know, we're train fans here. I love the BART. I think it's fantastic. First of all, they have a train to the airport, which we don't have. So any city that has that, I think is great. But also you can get a lot of places on it. I went to San Francisco, never rode in a car the entire time. I was there for a week, took trains everywhere. It was great.
That would be great. I have not ridden on a BART when I went to San Francisco, unfortunately, since I was just passing through. But I completely agree. Any city that has a train that goes from the airport really to anywhere, I'm like, hopefully downtown, is already off to a good start.
So in the early 1960s, BART looked at the feasibility of running train tracks over the bridge or building a new lower deck. But the conclusion of that exercise was that it wasn't advisable. So that has not been installed to date. This is also sad, but I think it's worth noting. The bridge is the most used suicide site in the world. If you manage to survive the 4-second fall, you would unfortunately hit the water at 120 kilometers per hour. Of the 5% that survive the fall, most die of hypothermia in the cold water and or the very strong currents. A suicide barrier netting is under construction and scheduled to be completed this year. But please, if you're struggling with mental health, don't jump off this bridge or any other bridge. Please get help. There are people out there. Please get help. Don't jump off the bridge. Not worth it. The Golden Gate Bridge is designed to withstand 109 km per hour winds and has been closed on 3 occasions where wind exceeded this speed. As much as it sucks to have the bridge closed, I think that's a really safe thing that they're doing to say, whoa, we're past our limits, close the bridge. I like to see that. As part of the suicide barrier project, the walkway railing is being replaced with a thinner, more flexible slat railing, and that improves the aerodynamic tolerance up to 161 kilometers per hour. What happens is the railing along the walkway doesn't have enough openings in it, and so it's kind of creating a sail, which is not helpful. So the one that they're replacing it with has a lot more free area, a lot more of it is open, and that allows the wind to pass through and have less force on the bridge itself, which is why it can handle the higher wind rating. Nothing comes without consequence, though. These new slats create an aeolian tone, the sound produced by air flowing past a sharp edge, and it can be heard on both sides of the bridge. But honestly, it's a small price to pay. The bridge is close to the San Andreas Fault, and the area is prone to earthquakes. San Francisco and a lot of California are very prone to earthquakes, and not to give away when we're recording this, but there was actually a very large earthquake in Turkey this morning that had devastating effects, and seismic design is something that we're hoping to talk more about in the future. It's been on the list for years. It's a really interesting topic. I don't know a ton about it at this point, but it's something that we've been brainstorming and talking about. The Golden Gate Bridge is in the process of a seismic upgrade to withstand a significant earthquake with only minimal damage. And that's usually what seismic design is intended to do. It's meant to prevent catastrophic failure, and so it has to allow some kind of movement. But there's usually still things that will break or crack, so the drywall may break or crack, but the building stays standing. So the drywall can be replaced. Replacing the entire building is obviously a lot less safe and a lot more expensive. And the Golden Gate Bridge was designated a California Historical Landmark in 1987 and a San Francisco designated landmark in 1999. So it's not going anywhere.
So there you have it, the Golden Gate Bridge. Ahead of its time, it was the longest and tallest bridge when it was built, bringing much needed growth to San Francisco and economic relief to the U.S. during the Great Depression.
For photos, sources, and an episode summary for this week's episode, head to failurology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failurology so more people can find us. If you want to chat with us, our Twitter handle is @Failurology. You can email us at thefailurologypodcast@gmail.com. You can connect with us on LinkedIn, or you can message us on our Patreon page. Check out the show notes for links to all of these. Thanks again to everyone listening, and tune into the next episode where we're going to talk about the Tacoma Narrows Bridge. Like I said, we're going to talk about it on an episode very soon. And while we don't normally like to do two similar episodes back to back, so while we normally wouldn't do two bridges in a row, as we were researching the Golden Gate Bridge, we were wondering about the Tacoma Narrows, and there's so many things that connect the two together. So we thought we'd go for it. So tune in next time to hear more about the Tacoma Narrows and why it is such a famous bridge in the engineering world. Bye, everyone. Talk soon.